Hi, everybody. The past couple of weeks, we've learned all about different four-sided shapes. This week, we're going to be focusing more on comparing different shapes together. So in the Scale Ella video, which I think is hilarious, you took a look at scale factor. In this lesson, we're going to look at another way that you can compare shapes other than scale factor. By the way, my favorite part of the Scale Ella video is when they size up her fingers after they've sized up the phone just to make sure that she can continue to text message. So that's my favorite part. I'm curious if anybody else has favorite parts. So one way that you can compare stuff is using a ratio. So there's different ways to write out ratios. If there's like a 1-to-2 ratio, you can write it with a colon, or you can write it in words, or the most common way to write a ratio is actually just as a fraction. So that's a 1-to-2 ratio. And then a proportion, you'll see in my next example, is just an equation that compares two ratios. So let's take a look at one of those. So number one, it's asking you to solve a proportion. This one, many of you might look at and say, oh, I've already figured out what x is. And if that's the case, it's because you used proportional thinking. You saw that 18 was 3 times bigger than 6. So then you might have just asked yourself, well, then what's 3 times bigger than 5? 15. So x is going to turn out to be 15. But they won't always work out quite this easily. The numbers might be messy or the algebra might be more complicated. So you probably have learned a strategy at some point called cross multiplying. The fancy geometric name for this is actually the means extremes product theorem. It says that if you take the bottom left denominator and multiply it by the top right numerator, it always equals what you get when you take that top left numerator and multiply it by the bottom right denominator. But most people just call this cross multiplying. So if I multiply my yellows 6 times x, that's just 6x. And the theorem says that's equal to what you get when you multiply 5 times 18, which is 90. And then you just do a quick solving, divide by 6, and you'll get that 15 that I showed you before. So sometimes you can solve these problems without doing cross multiplying, but that is kind of the method that works every time you're solving a proportion. So let's take a look at one that's more complicated. You can see that proportional thinking isn't really going to work as well for this one. So I'm going to multiply those two together. I'm going to start with those because that seems a little bit quicker and easier. 22x. These ones seem more complicated. So you have to remember to multiply the 12 by everything in this bottom left denominator. So what I do so that I don't forget that is I actually set it up just with parentheses. And then I do the distributive property. So some people do that step in their head and realize they have to do the 12 times the 2x and the 12 times the 1. But I like writing it out just to make sure that I don't miss any steps. So 12 times 2x is 24x. And then the part people forget is that you also have to multiply the 12 by the 1. And then be careful when you're solving. You don't always subtract the smaller x. The 22x is alone on the left, so we want to leave that where it is. I actually want to subtract 24x from both sides. So I get negative 2x equals negative 12. And then I divide by negative 2, and I get x equals 6. And I can always double check and see if that works when I plug it back in. If I plug 6 back in, I obviously get 6 in the numerator. 2 times 6 is 12, minus 1 is 11. 6 elevenths is equivalent to 12/22 if you simplify. So it does work if you plug it back in. These just aren't that easy to substitute back in. All right, let's do one more. This one actually looks a little simpler than number 2, but there's something about it that's a little trickier. See if you can figure out what that is as I'm setting it up. Oh, it's going to be that part. What is x times x? Well, when you multiply something by itself, that means you're squaring the number. So this is actually x squared equals 36. And then you can solve a problem with x squared by taking the square root of both sides. So square root of 36 is 6, because 6 times 6 is 36. But you have to be a little bit careful. There's actually 2 answers. So 6 times 6 is 36, but negative 6 times negative 6 is 36 also. So the solution for this is actually plus or minus 6. And what that means is it means x is 6 or negative 6. Either one works if you plug it back in. Plug positive 6 back in for both x's and you'll get an equation that's true, or plug negative 6 in for both x's. And that equation is also true. So don't forget both solutions. All right, what does this look like in real life? I would say out of all the math skills that I use regularly in my everyday life, it's solving proportions. So I use proportional thinking a lot. So one of the places I think that's come up is with COVID data. So if we look at the world population and then we look at the number of COVID cases that there have been in the world, then we can look at the US population and say, well, how many cases should we have if what proportion of the world's cases should we have? And then we can see if we're doing better or worse than we should be doing. The thing that's complicated with this one that I didn't make as complicated in your homework is the population. This one's 7.8 billion for the world, and this is 328.2 million for the US. So I'm actually going to change 7.8 billion. That's actually equivalent to 7,800 million. I put a lot of thought into how I wanted to set this up, and I think that is going to be the easiest way. So let's go with that. So the key thing with these proportions is there's a bunch of different ways to set them up. You just need to make sure that you're consistent. So I'm going to make one fraction about COVID cases in the world. So I'm going to say there's 99.3 million cases in the world out of my 7,800 million people. So I did cases on top, population on the bottom. So that means my other fraction, I need to make sure that I also do cases on top, population on the bottom. So the cases is what we don't know. The population is what we do know, 328.2 million. And then what I don't know, the number of cases, I'm going to put X. So for these, it's the setup that's the trickiest part. And then I can do my cross multiplying. But see how we were consistent? It was number of cases out of total population equals number of cases out of total population. So I'm going to cross multiply. I'm going to get 7,800x. And then I need my calculator in order to cross multiply that one. 99.3 times 328.2. I got 32,590.26. And then I can just divide both sides by 7,800. And that is going to give me my solution. All right, normally I don't like using decimals when I'm dealing with number of people, but remember that this is actually in, and I'm going to put a squiggly equal sign because this is approximately 4.178. This is in millions, how many millions of cases, so I'm okay with doing the decimal. So it's approximately 4.178 million cases. All right, so let me look up and see how many cases the US actually has to see how we're doing. So if we were on pace with the rest of the world, we should have 4.178 million cases. We have, as of today, 25.2 million cases. So that's why people have really been talking about how the US haven't handled this so well, because that's way more cases. That's like 6 times more cases than what we should be on pace to have compared to the rest of the world. So I have found that a lot of proportional thinking has been used in talking about COVID and how different countries have been dealing with it. So that was one example that I wanted to show you guys. Another place that I use proportions all the time is when I'm watching sports. I'm constantly thinking about, ooh, they've scored this many points so far. How many points are they on pace to score for the rest of the game? Or when you look at like stats, oh, that person has scored this many 3-pointers in their career so far. Are they on pace to break any records? So I wanted to show you this quick calculation. I'm constantly thinking about this when I watch games. So you guys know I'm a big Illinois basketball fan. So if they have scored 21 points 13 minutes into the game, one thing you need to know is games in college are 40 minutes long. I can put these fractions in whatever format I want. I just have to be consistent. So I'm going to go with 21 points for 13 minutes. So I'm going to set mine up using points and minutes, but that's not the only way to set it up. But I'm going to say they've scored 21 points in the 13 minutes that they've played so far. How many points? So that's my X for how many points in a 40-minute game. And then let me do my quick cross multiplying. 13X 40 times 21. Let's see what that is. 40 times 21 is 840. And then I'll do my quick divide by 13. They're on pace to score about 64.6 points. You can't score a fraction of a point in a basketball game, so they're on pace to score like about 64 or 65 points in the game. And then, as you know, that doesn't always turn out to be true. Sometimes they go on a cold streak, sometimes they go on a hot streak, but that's always what I'm thinking about when I watch basketball games. All right, let's do one other one where the setup might not be quite as straightforward. We've got a 60-meter pole, and it's split into two parts in a ratio of 11:4. Here's the problem with that ratio, though. When I add up those two parts, that doesn't actually add up to 60. It adds up to 15. So when I set up my proportion, I don't actually want to go 11:4 because then where does the 60 go? The 60 is the total length. The 11 and the 4 are the two different parts. So I actually want to do something like 11 out of 15. So that's like the 11 is the long part and then the 15 is the total. And then that way I have a place to put my 60. That's the total length of the pole. And then some of you might be thinking back about example number 1 and saying, oh, I can just do this one with proportional thinking, or we can do a quick cross multiplying. 15X, I just lost my pen there for a second. Equals, and then 11 times 60, I think is 660. And if I divide, that should be 44. So 44 is the long part. 44, were there units on that? I don't even remember. 44 meters is the long part. If I want the short part, I can just go 60 minus 44. So that's 16 meters for the short part. And then it asks for the difference. It says, how much longer is the long part than the short part? So to answer the final question, I can just go 44 minus 16. And let's see, how much longer is that? It is 28 meters longer. So look for that to come up in your homework problem too. If I give you a total and then I just give you two parts, you might have to find the total of those two parts. 11 and 14, 11 and 4 added up to 15. So we had to set up our proportion using 15, not just the 11:4 ratio that we were given. So look for that to show up in a homework problem too. So that's a good sampling of ratios and proportions. Next week, we're going to look at how scale factor and ratio and proportions all come together and take a look at similar figures. But for now, you're ready to do some practice for week 21, homework 2. Let me know what questions you have. Bye.